Okay, so it is time to start. So obviously, everyone's been to lab, so you know that we have a taste lab next week, but when you come to the lab report is due, not on a flash drive, not on a whatever, can I email it to you? Please plan ahead. I know what it was like when a paper is due as a student. That is exactly where a computer crashes, a flash drive fails, a printer is out of ink or otherwise incapacitated. So do plan ahead so that you have it printed and ready to go. When you come in class, just put it at the front desk, all right? All right, any questions about that? It'd be a short lab and then you'll be able to get out in time to study because we have our exam coming up, okay? Now, saying that, the next chapter that will probably start maybe Wednesday of next week, because we still have stuff to cover in this chapter here, is peripheral nervous system physiology. That will be a lot of repeat of the neurotransmitter chapter, so that'll go pretty smoothly. But if you're trying to study acetylcholine signaling and epinephrine signaling via their receptors, all right, if you go here where we have the taste lab, all right, it says here, peripheral nervous system flow chart, it's all there, okay? In fact, I'll just show the key, back out of that, go back to the key where everything is, and I'll point out some things that you don't have to worry about. You don't have to worry about this, okay? Because that's not part of the test on Friday, okay? Voluntary motor responses, that's acetylcholine signaling, all right? Acetylcholine, nicotinic cholinergic receptors. Involuntary is all over here, cardiac, smooth muscle, and glands, and then it's divided into your rest and digest, and put it in nice cool blue because you're supposed to be cool and calm. And then over here, danger, danger in red, sympathetic or fight flight. And don't worry, you don't have to worry about the nerves. That we're going to cover in the next chapter. So don't worry about that. But these things we talked about, that's all there. Okay, and then don't worry about those nerves. We didn't cover that, but this is what happens under those systems. And then everything that's parasympathetic works by the same neurotransmitter and receptor. And then over here, epinephrine, known as adrenaline, works by 3 different receptors. And so you just got to remember beta 1, think one heart, beta 2, think lungs, or best to get away, blood supply to skeletal muscles, or alpha. So that is, there's a blank flow diagram for helping to study that. And then the key, of course, right? Flow diagrams help if you practice them. So I did want to make sure and let you know that resource was there as you are studying. Any questions about that? So we've got time, all right, because we are here, 11th. And then we got all next week to keep studying. Short lab, all right? And so if you are having difficulty with material, please contact me, all right? Talk to me in lab next week because it's a short lab. If you do have questions, now's the time, okay? And what I probably will do is I haven't written the exam yet, but let me get to my PowerPoints here, is once I write it, which will be this weekend, I will let you know what questions are going to be on the exam. I'm not even bullshitting you. I'll say there's this many questions on acetylcholine signaling and its receptor, this many on epinephrine and its receptors, there's this many questions on, you know, whatever metabolism, this particular thing. I'll break it down to you so you know exactly what you got to study. Then you just have to study it. I'm totally into being transparent. When I say there's no trick questions, there's not. I'll even tell you what I'm going to ask, not word for word, but I said this many questions on this topic, this many questions on that topic. Then you just have to study it. Okay, so I'll be able to give that information to you in lab. Thus, if you have any questions, we have a short lab. You can ask them. Okay. All right. I want you to really do well on this test. I know it's a lot of material, but I want you to do well. So let me see what my volume is doing. I brought an exterior mic because I was sick of all the crap that this HDMI cord was doing to me. So I'm going to see if I can get things to work today. So I'm going to go back to, and this will be my test. All right, make sure my volume's up. Okay, so, and make sure my volume up is up on my computer. Okay. It should be up high, high, high. All right, let's give it a try. So I want to go back to the YouTube videos to see if my setup is working. I turn the volume up a little bit. My volume is probably too low. There we go. Let's try that now. Come on.
Okay. Are you having pain anywhere?
No.
No? You feel pretty good in general?
Yeah, yes.
You can understand what I'm saying to you, right?
Yes.
This was the
Can you
Broca's
close your
aphasia
eyes
guy.
for me? Perfect. Now tell me your name.
Good. Cause I've had no
I don't know why
Can
I'm
you
saying
tell me
iPad.
what city we're in right now? This is Richmond. Can you say Richmond? Richmond. Say Richmond.
He said Virginia.
Can you say 1, 2, 3?
1, 2, 3.
Okay, that's very good. Can you name the weeks of the days of the week for me?
Yes.
Name the days of the week.
Monday, Tuesday, Wednesday, Friday, Saturday, Sunday.
I won't play the whole thing, but you get the idea, and you can see the frustration on his face. He knows language. He knows what's being asked of him. He knows the answers, but getting it out with Broca's aphasia is very difficult. So as nurses, like this guy who's working with him, which might be a speech language pathologist, is very patient. His voice is very soothing and calming, and, you know, don't act like, come on, spit it out. Don't do that, okay? They feel bad enough as it is. Okay, so let me close that one down. And then we'll look at, close that down. Then we'll look at Wernicke's aphasia, where it's called fluent aphasia because the words come spilling out easily, but they make no sense. They're not, the people aren't tying the words together in an understandable sentence. And so it's very different. Oh, commercials.
All of Injury's management.
Gotta block the sound on that. Okay, so fluent aphasia.
Hi, Byron, how are you?
I'm happy. Are you pretty? You look good.
What are you doing today?
We stayed with the water over here at the moment, talk with the people for them over there. They're diving for them at the moment. They'll save in the moment. He'll have water very soon for him. With luck for him.
So we're on a cruise and we're about to
We
get to
will
Juneau.
store it right here and they'll save their hands right there for them.
And what were we just doing with the iPad?
Right at the moment, they don't show a darn thing.
With the iPad that we were doing. Like here?
I'd like my change for me and change hands for me with Happy. I would talk with Donna sometimes. We're out with them. Other people are working with them. I'm very happy with them.
Good.
This girl was very good and happy. And I play golf and hit other trees. We play out with the hands. We save a lot of hands on hold for people's, for us, other hands. I don't know what you get, but I talk with a lot of hands for him.
So obviously all his emotion is there, and it sounds like he doesn't realize that what's coming out of his mouth doesn't make sense. Again, it calls for a delicate touch and patience. It's just a disorder in the Wernicke's area, okay? And you're gonna see people like this, all right? It could be a result of brain damage from an accident, a stroke, something like that. It could just be something that starts to happen as people who are prone to it, dementia sets in, because this woman that I know that's got some dementia, she is losing her language ability. She talks, I've known this woman for decades, and when she talks to me, I don't know what she's trying to say. And she's happy like he is, you know, and the words come flying out, but it doesn't make any sense anymore. So you're definitely going to see stuff like that. I mean, has anyone ever encountered anyone with an aphasia? No, you'll see it in the hospitals. Okay, so we went through this. I think this is where I left off. I left off with the sleep twitches. All right, when GABA is trying to get a control of your muscles and paralyze them when you're in deep sleep. And that's a process that doesn't happen very quickly. It happens over time, and you might experience those myoclonic jerks when GABA doesn't quite have control of your skeletal muscles yet. All right, so now we're continuing with the cerebrum. This is all cerebral stuff. All right, and then we'll get on to the lower brain regions. But I'm actually going to cut a couple of these off because I've been looking on the internet and our textbook doesn't cover it very well. So I'm going to cut down these two nuclei, deep cerebral nuclei called ganglia, and then just focus on these two, which will make it nice and easy. But the reason I have for the claustrum right here, which is this little line, they're not colored like this in the brain. I color coded it to make it easy. It's got a pair of eyes. So the week after next week, we're going to be doing a sensory lab, and you're going to be testing the function of this nuclear cluster right here, because that provides visual feedback for autonomic control of the muscles involved in balance. And you're going to find, and well, if I fall on the stage, you get a good laugh, okay? And plus I'm wearing slight heels makes it hard. That if you're standing, even if you stand with 1 foot, you should be able to do things that balance yourself, okay? But if I close my eyes, oh boy, okay, not so good, because you need visual feedback on the horizon, and that feedback goes into your brain to all the motor areas that control balance muscles. And if you don't get that visual feedback, it's very difficult to keep your balance, all right? So the claustrum is visual feedback for control of muscles autonomically, if you're not thinking about it. If you don't get the visual feedback, you have a hard time keeping your balance. Now the caudate nucleus, I got a guy walking, okay? Now, we're all past the toddler stage and infants are learning to walk, but their brains are forming and they're learning in many places in their brain, their frontal lobe, motor cortex, their cerebellum, which stores learned muscle motor patterns, and then this nucleus right here, okay, next to your lateral ventricles, it doesn't matter, but you learn how to keep your balance as you're walking. So as an adult, you don't think about it, you just, well, what's happening? I'm not thinking about it, I'm doing it now. Is my arms and legs are rhythmically moving in opposite each other. So if I'm thinking, now I'm thinking about it, I can do it. What walking is controlled falling. And as you take a step forward and land on this leg, your center of gravity has now been pushed there, forward. And you could fall over. Your arm, without thinking about it, because you've learned these motor patterns in the caudate nucleus, swings back as a counterbalance to kind of provide little mass back here so you don't fall forward. All right, so the caudate nucleus is responsible for that rhythmic swinging of the arms and legs. It's to maintain balance, and it's autonomic. You don't think about it. Once you learn how to walk, it's there, okay? Now, they learned that this is important in people who have Huntington's disease. I think I might have a reading supplement in here. I can't remember, but that's what they do. All right, so I'm going to cross off a couple things here. I'm going to swing this around so I can write a little better. All right, so these deep cerebral nuclei, claustrum, different pen color, provides visual feedback, which is very important. For that should be an autonomic motor control for balance. You don't think about it, but you'll see in lab when we try all the different foot positions and eye open, eye closed, that you're going to see. Now, some people are very trained to, if you're an athlete or a dancer, you might have fantastic balance with your eyes closed. Now, the thing that strikes me is if you encounter a patient, that loses their vision, and they didn't grow up that way, they're going to have lots of challenges in their world. But walking is going to be one, and balance, because now, I mean, if both feet are on the ground, but as soon as you're lifting a leg up to move, and I'm not going to do it because I know I'm on a stage and I'll fall off. All right. Keeping your balance as you move about is going to be very difficult because you've had that visual feedback. And then when you lose it, so we'll cross these off because they're not that important. But the caudate nucleus is for autonomic, I keep putting an N, autonomic motor control of the rhythmic swinging of your arms as you, I say, walk, run, whatever. If you're moving, using your legs, your arms are going to be swinging to keep your balance. But you're not thinking about that. That's happening autonomically. And they found out this was very important because people with Huntington's disease, which I talked about briefly before, the autonomic, not autonomic, the, what am I thinking? Well, anyway, the dominant disorder, where if you inherit one allele for this trait from mom or dad, you're going to express it. And it doesn't show up until you're in your 40s. And it's a gradual loss of neurons here that is associated with Huntington's disease. They're not saying it causes it. They're saying, wow, we see a lot of loss of neurons in this particular area, and they know where it's located. And like if they put them in an MRI scan, see these neurons deep inside your brain are pigmented. Okay. And so they show up dark. And if you have someone who's displaying signs, and you can do a genetic test and find out that they have Huntington's, and you can maybe just tell how serious it is based on their symptoms. But if you do a brain scan and you look at this area and it's bleached out, those neurons are gone, that's pretty much definitive along with the genetic test. All right. And once that's gone, it ain't coming back. All right. Neurons don't have a great way to regenerate themselves. Not yet as of that. We don't know. Okay. So degeneration of neurons in the caudate nucleus, one of the deep cerebral basal nuclei, occurs in Huntington's disease. It produces chorea, which is a disorder of uncontrolled jerky movements. I think that the fancy word for it is dyskinesia. All right. And then they talk about Parkinson's, but Parkinson's has nothing to do with the caudate nucleus. Okay. All right. Now the limbic system and the cerebrum. So they do talk about it a lot on page 60 of the wiki text, but the amygdala, and they wrote it wrong in the textbook, and I made a little note, they spelled it wrong. The amygdala is, yeah, I'll just say functions in fear and female orgasm. That's not in the textbook, but I know it because I teach a course called Biology of Sex. They put people in an MRI, not an MRI, a functional magnetic, no, not that, a PET scanner, that's right, positron emission tomography, where in real time, they inject people with a radio labeled glucose molecule. And if on the scan, parts of the brain show up as bright reds and yellows, it means that's areas of the brain that are very metabolically active and are working. All right, if they're dark, they're not. All right, I think I showed you a PET scan of someone with Alzheimer's and their brain looked dark. Well, when they put women into one of these scanners and asked them to have a real orgasm versus a simulated one, when they had a real orgasm, this part of the brain shut off and got dark. If they were faking it, it stayed active. All right, interesting stuff that some scientists get to do. But also, if they show patients, just people, images that are fearful or provoke fear, this area of the brain lights up. So when we talk about fight flight, okay, there's centers in your brain that play a role in that, and they light up and become active. Now the other, and I say nuclei because there's a left and a right, all right? The cingulate gyrus is responsible for forming associations between, and this one's interesting, behavior, I'll say behavior outcomes. Okay, so if you do something and get a reward, you do it again. Okay, and I'm going to continue this because I don't have room for it because I'm going to have another nuclei under that. So I'm going to go up here. Likewise, if you do something and you get punished, or something bad happens, you avoid that behavior. So think about kids growing up, all right? We form as humans tight associations, and that's how we learn to navigate in the world, what's okay and what's bad for you, what's dangerous. So this is all autonomic, and it's there to protect us. So if a kid, I just use the kid example, in parenting, a kid does something, and as a parent, you don't like that behavior, that's a bad behavior, or let's say that behavior could hurt the child. You punish them, you're like, no, don't do that. All right, okay, and they got a negative response from that behavior. They tend to avoid it. It might take a while, but eventually they'll form the association. If they do something and they get hurt, like they touch something and it's hot and they burn their hand, that's a negative outcome to their behavior, and they're not inclined to do that again. They will avoid that. If you do something and you get praise, yay, good job. Even us today as adults, we are like, oh yeah, I'm gonna do that again. All right. Or if you eat something or do something and it feels good, that's a positive outcome, and you form an association. Okay, I want to do that again. So that you realize how strong of an impulse that is in us and other animals. All right. So that's an important nucleus. Now the septal nuclei reinforces pleasurable behaviors. So whereas the cingulate gyrus does both positive and negative outcome association, so avoid this, or I want to do this again. This one is simply reinforcing if you do something that's pleasurable, eat something, act a certain way, and you get a cookie, figuratively speaking, or literally, it will reinforce that pathway and you do it more and more and more again. Now I'm going to test you here. How is this reinforced? It probably involves release of a neurotransmitter, one we've talked about. What's the neurotransmitter that I said is part of the mesolimbic blank system? Because this is the limbic system. And when I say you do something pleasurable and you get a wave of this neurotransmitter being released, dopamine. It's associated with addiction. All right. So this in your brain is what ties and reinforces pleasurable behaviors with their outcome, probably because of a dopamine release. Okay, now the hypothalamus. Let's see, do I have? Okay, I left spaces. So the hypothalamus and the thalamus. So in the brain, the hypothalamus is below the thalamus. I know you took it in anatomy, but the hypothalamus does a lot. We've talked about it already a lot. Remember how the hypothalamus has a set point for body temperature? And if it goes too high or too low, it's going to stimulate either skeletal muscles to shiver or sweat glands to sweat to cool you down. There's a nucleus in the hypothalamus that does that. I'm going to introduce that to you. And we talked about the importance of the hypothalamus and the oxytocin release. So the hypothalamus has many nuclei. That's an N, nuclei. And it functions in the 4 F's. All right. Feeding when you're hungry. That's a strong impulse. You want to eat. That's all you can think about when you're hungry. Fear, fight, right? Literally your fear flight system. Your hypothalamus is what stimulates the epinephrine release in your body in the fight flight response. So when I say that, fear and fight, that's literally your sympathetic nervous system. Your hypothalamus controls that. All right. It also controls, when I say 4 F's, go away. I'm going to use the pretty word, fornication. It controls everything to do with reproduction. Everything. When they say the brain is the sexiest organ, it's true because your hypothalamus is in control of everything. So those are the 4 F's. And we'll talk about those nuclei in a little bit. The thalamus functions as a relay station. Do you know what I mean when I say relay? Do you know what a relay race is? A relay race is when you have runners in a competition and one runner goes so many treks around the track, and then another runner is going to take their place and they literally pass the baton, and then the next runner goes. And that's what their thalamus is. It's a relay station. And so what it does is it sorts info going up or down the brain. Okay. So as I am here walking around, moving, things like that, I have sensory receptors in my joints. Okay. We'll talk about this next week, but 2 weeks from now in lab. And I'm not aware of it, it's autonomic, but they send information about my joints, whether extended or flexed or whatever, or how much weight is on the joint or where I am in space. And that information goes up from those muscles and joints, up the spinal cord, up to the thalamus in the brain, and the thalamus will send it to where it needs to go. Okay, this is motor stuff, so some needs to go to the motor cortex and the frontal lobe. But we also have to send some information maybe to the caudate nucleus, all right? Maybe to the cerebellum. It's going to send it to where that information needs to be processed. Likewise, if you have a motor command that's up in the brain, that's issued from up in the brain, that goes down the spinal cord and out to your body. All right. The thalamus is sorting where it needs to go. So when it comes up, if it's sensory, it's going to go to the thalamus, and the thalamus is going to send it to what cerebral lobe that has a sensory cortex. Which one of the 5 has a sensory cortex that will interpret that sensory information and then issue a command if it's needed. Parietal lobe, right? So that's what's happening. It's sorting it. It's like a post office box, you know, it's a post office station. Information comes in, it gets sorted to where it needs to go. That's what it does. And that's probably the last I'll talk about on the thalamus. Okay, so we've covered a whole hell of a lot. So now we're going to move down. So technically the thalamus and hypothalamus are part of the diencephalon. That's just underneath the cerebrum. All right. I'm not going to say more about the thalamus, just that it's a relay station, it's sorting stuff. And we will look at a couple examples of that and some disorders of that sorting. But the hypothalamus, I'll spend more time on because we've already learned a lot about it. We've learned that it causes the secretion of oxytocin and it controls your body temperature. All right. So I have, do not memorize this. This is meant to show the sorting at the thalamus. So let's say you touch something. All right. And maybe it's not a bad sensation, you just touch something. Well, you have touch receptors. They go into the back part of the spinal cord, they travel up the spinal cord, and they go up the brain regions from lowest to highest. We're going up the medulla, the pons, the midbrain, and in the diencephalon, okay, we have the thalamus here. And so there's a left and a right. And it says, don't ask me how it knows, I don't know, but it's like, this is sensory information. Oh, I know where this has to go. This has to go to your sensory cortex and the parietal lobe. All right. If it's something else, then it sends it to another part of the brain. So that's how it's sorting information. So when we have that sensory lab and we do the 2-point touch discrimination test, which is actually a real test in medical testing, this is what your brain is doing. Sensory stuff goes up the spinal cord, goes up to the brain, goes to the thalamus, and then goes to the sensory cortex to be interpreted. Don't memorize this, but you learn, believe it or not, here's your thalamus, and below it is the hypothalamus, and that's your pituitary gland, your optic chiasm. But we're going to pull out and talk about some nuclei and what they do. Not all of them, some of them. So, okay, the paraventricular nucleus secretes oxytocin. Okay, the supraoptic nucleus in the hypothalamus secretes ADH. Does anyone know what ADH stands for? Antidiuretic hormone, ADH. So that is going to regulate water balance. That's going to cause your kidneys to retain water and not let it out in the urine. So this is how you concentrate your urine. All right. So we're going to do a P lab this semester. Yes, we are. Where we're going to be looking at ADH secretion in some students, like half the class. So if you are dehydrated, you've gone all day without drinking anything, or maybe eat something really salty or drink something salty. All right, have a couple pieces of pizza. You ever notice that you're thirsty after, right? Well, I'll talk about that nucleus in a second. But what's going to happen is your brain, your hypothalamus, has a set point for blood saltiness. All right, so I'll put here. hypothalamus. Come on, pen. Has a set point for blood saltiness. And that's just a very crude way of saying blood osmolarity, right? Your blood salt content. And if it rises too high, the hypothalamus senses it, sensor, integrating center, and effector, and it secretes ADH. Now, you know anyone who's taking diuretics? Family member who's taking diuretics, anyone? No, we usually get at least one person in the class. Diuretics are called the water pill. They're given people who have high blood pressure or have edema. And what the diuretic causes to happen, it causes you to pee a lot and pee out body water. And so then you get rid of that body water, your blood pressure goes down, or if you've got edema, you lose that body water, so the swelling goes down. And anti-diuretic makes you not pee. I'll put here, makes kidneys retain water. So instead of losing it out in your urine, you're keeping that water in your body. And by retaining water, it will dilute the salts that are in your blood and it'll bring it back down to normal. We'll talk about this in a lot more detail in the cardiovascular chapter. All right, but ADH. Okay, now for the anterior nucleus, right down here, I've got a thermometer, which is for temperature. So your anterior nucleus regulates body temp. We already learned this one. I just said the hypothalamus regulates your body temp. Well, it does it through the anterior nucleus. So when I think of the anterior nucleus, here's what helps me remember. I see the word ant, and I think Antarctica, which is a cold continent, right? Antarctica is cold, it's very cold. That's a temperature. So I remember anterior nucleus, Antarctica, cold, that's temperature. So if you come up with creative ways to remember these things, it does help. Now, the ventral medial nucleus of the hypothalamus controls all these things. And that's why I gave you the 4 Fs. So it's your fullness center. So when you've eaten and you're full, you're like, time to stop eating. Some people think that people who struggle with obesity, there's probably genetics to it and lifestyle certainly, but they might have a problem with the ventral medial nucleus of the hypothalamus. They just don't feel full. It's also for fear and aggression, that could be fighting, and all things reproductive. So the 4 Fs are feeding, regulating feeding, like when you're full, you stop. And then of course, fear and fighting, literally your fight flight system. And then all things reproductive, including fornication. I could use the other F, but I won't. Okay, so hypothalamus does a lot. Now, when you're hungry, I just say hunger. That's why a person diving into a piece of cake. That nucleus is stimulating you to eat because you're hungry. Also a very strong impulse. I remember that because it's got the words ATE or 8 in it. So lateral nucleus, that's 8 is in it. Now the preoptic, I don't have a cool thing to remember with it. If you come up with one, please share and let me know. But I've got a person who's obviously thirsty and there's a glass of water. So the preoptic nucleus stimulates the thirst response. So if you're dehydrated or you've had something very salty, that urge, oh, I gotta have something to drink. I'm just dying. I gotta have something to drink. That's a very strong impulse. That's the preoptic nucleus. And then the last one, I've got someone sleeping in bed, suprachiasmatic nucleus, and this is the last one, thank God, regulates your sleep-wake cycle. That's known as their circadian rhythm. You don't appreciate this because wherever you are, what latitude you live at, your pineal gland plays a role in this, but anyway, you have a sleep-wake cycle, a sense of daylight and nighttime when it's time to sleep. If you've ever gotten on a plane and traveled outside your time zone, where they're like 5 or 6 hours ahead or behind or whatever, and when they're just ready to get up in the morning, you're like, it's nighttime, it's time to sleep. That your circadian rhythm has been set to your time zone, and you've now traveled out of it, and then you notice that you had the set pattern, and it does go away after a couple of weeks. All right, it'll reset to wherever you are. Okay, so that's a lot of nuclei, and that's not even all of them. I think there's 9, and I covered a few. Okay, we're getting there. Okay, your midbrain, tiny, tiny little part of your brain. Very important functions. Nuclei for autonomic body responses. So remember in anatomy, you had to learn these structures back here at the posterior of the midbrain, and there were 2 bumps, all right? I think collectively they were called the corpora quadragemina. Well, the 2 bumps are the superior and inferior colliculus. 2 tiny little things in the brain, but boy, do they control some reflex responses that are important. Okay, the superior colliculus regulates autonomic responses to vision. I just say vision, that's fine. I was going to say visual cues, but that's too much. The inferior colliculus regulates autonomic responses to sound. Okay, so anatomically, if you're looking at someone, what's more superior? What's higher up? Your eyes or your ears? Which is a little bit higher. Eyes, okay? So remember, superior, your eyes are superior to the ears for hearing, okay? So the superior colliculus is for involuntary responses to what you're seeing. And then inferior, if they are lower, reflex responses to sound. These can be saving your life, and you don't realize it, okay? If I were to take, okay, this is bigger, all right? If I were to take this mouse and just chuck it into the middle of the auditorium here, without even realizing that your eyes are tracking this moving object and looking at its trajectory, you're analyzing its trajectory. And if it looks like it's going to land on you, you're going to, and you do it like that. Driving in your car, okay? I drive into work. There's a lot of logging trucks out there. And every now and then this happens. It's not necessarily a logging truck. It could be another person driving the other way. It's early. They're not paying attention. They're messing with their, I don't know, Dunkin' Donuts, whatever, coffee, whatever. And I notice that they're starting to veer into my lane. And I'm already hitting the brake and pulling over a little bit. And then they correct themselves, right? But without even thinking about it, your eyes are tracking the trajectory of moving objects in case it's life-threatening for you, and you'll make responses, all right? That's the superior colliculus. It looks so small. Oops, sorry about that. But, okay, so this person over here doesn't have a very good functioning superior colliculus because obviously they see that ball coming, they're not ducking. Any normal person with a normally functioning superior colliculus is going to either catch that ball or dodge away from it, all right? Now for inferior colliculus, you can't hear, and I couldn't get a GIF that had a sound. What's happening to these guys is there's a guy in a truck behind him with a really loud train horn. And when he blares it, this happens to you, probably all happened to you. I mean, if walking on campus, we're all looking at our phones, right? I'm just as guilty. But when you cross a road, hopefully you stop. But if you're not, you're on your phone, car's coming, blah, they blare on the horn, you go like this. That is an autonomic response to sound. And what you tend to do is you tend to face it because you've got all of your senses now focusing on a possible danger to your life. All right, you're sitting here, maybe a fire alarm goes off. A lot of you won't just sit, continue like this, you go like that. You'll turn your head to the source of the sound. So I say, you'll turn your head towards an unexpected sound, because that could save your life. That's the inferior colliculus. We've all experienced it, but that's what's doing it in your brain. The red nucleus, I'm going to skip that one. But the substantia nigra I will talk about because The substantia nigra, which is here, and then the other side of the brain, it's there, secretes dopamine. And I think I explained to you how important dopamine is. The nigrostantial dopamine system, well, you tell me. We covered it in the neurotransmitter chapter. Do you remember what the importance of dopamine is in this particular system versus that? Fine motor control. Parkinson's, it's due to many things. It's a condition of low dopamine. And that would explain the motor disturbances you find in someone with Parkinson's, because you need that dopamine for the fine motor control. Now, the mesolimbic dopamine system, what was that about? And I just mentioned it before. And another deep cerebral nuclei. Addiction, all right? When you do something that feels good, you get a dopamine release. Drugs can do that. For some people, sex does that. You know, there can be sex addicts, there's food addicts, they could be addicted to almost anything. You could get a huge dopamine release. And that most of that dopamine is coming from this area. Now, if you have someone you think has Parkinson's, there's all kinds of tests that can be done. But if you scan them, CT scan or MRI, and the substantia nigra part of the brain is bleached out, those neurons are gone, they're not coming back. That could diagnose Parkinson's. Okay, so I had some gifts here. This was for the red nucleus, but I'm going to skip it. It's controlling your core muscles for posture, but I'm going to cut it. Okay, let me go back. Now, here is the brainstem. All right, that purplish thing that goes to the midbrain, goes through the pons, and goes through the medulla. That's the RAS. And they do want you to know that in nursing. The RAS stands for reticular activating system. Okay, quick little gratuitous review of neurotransmitters in this chapter. In deep sleep, your brain paralyzes your muscles so you don't get up and walk around. Your emotional brain is completely active. What is the neurotransmitter that's supposed to paralyze your skeletal muscles so you don't get up when you're in deep sleep? GABA, right? And I said GABA also quiets your mind to unimportant stimuli. Things you've learned in your lifetime, that sound or that smell or that thing, I don't have to worry about it. It's not a danger, it has nothing to do with me. I can sleep right past it. Okay. However, when you're in deep sleep, the reticular activating system can wake you up, can rouse you if an important stimulus is perceived. It could be smell, it could be sound, it could be anything, all right, that your senses pick up. And when that stimulus, that happens, the reticular activating system wakes you up because it could be life-saving. A fire alarm goes off, you wake up, you've learned it, your regular waking alarm, you've learned, I got to get up for that. My house, if a cat's throwing up and they're sleeping on me, that will wake me up just like that. I'll be straight up in bed. You hear a baby cry. Sometimes maybe you hear something crash in the kitchen, someone breaking into my house, right? That is the reticular activating system, and it's in all three parts of your brainstem to rouse you in case there's a life-threatening thing going on. And so we won't get to all of this today, but so getting back to addiction and dopamine. So you would probably have to, you could read this if you were online looking at this PowerPoint, you could expand the screen and make it bigger, but really all you need to know is all these drugs and many others not listed here cause a dopamine release and are associated with psychological addictions, which are very hard to break. All right, so cigarette smoke, smoking, vaping now, if it's got nicotine in it, it is addictive. All right, heroin, morphine, all kinds. We have an opioid crisis in our healthcare system, don't we? All right, any opioid-based pain medications, which are given to patients who've had surgery and whatnot. Yes, it handles pain very well. You get a dopamine release because you get a release from the pain, but they're very addictive. So be on the lookout. I mentioned this before, for patients who have had something, broken bone, other injury, something where there's been a lot of pain and they were prescribed opioid-based pain medication. And if it's been a month or two and they should be all healed up and good to go, and they're still asking for another prescription of that drug, that's an important patient history that you have to pass on to the doctor, because that's drug-seeking behavior, all right? And you have to stop that, because people can abuse it to the point that they die. I know someone on my street that had an addiction and he couldn't beat it. It killed him. Valium, very good muscle relaxant, all right? Because Valium does two things. It is a GABA agonist. Yeah, oop, nope, go back. Escape. Didn't mean to hit that. I need to go back. There we go. It's a GABA agonist, but it's also a dopamine agonist. All right. So people who take muscle relaxants, if they've been prescribed muscle relaxants, as a nurse who spends more time with the patient than often the doctors do, if they keep coming back for new prescriptions of this, and it's not for a condition that's being treated anymore, that's a problem. That could be drug-seeking behavior, and you're the people who are most likely to catch it because you're spending time with the patient and talking to them. And of course, all these other drugs, they all cause a dopamine release. They're associated with addiction. So the reason I went over that is because I want you guys as nurses to catch that kind of behavior, because you'll save a life that way if you catch them and they can get treatment, and certainly not be given that drug that they're seeking because they don't need it anymore. You might be saving a patient. Okay, so let me look at the time. All right, so we'll stop here at this and we'll continue with the rest of it on Monday. So the pons has a reticular activating system. It has two respiratory centers, the pneumotaxic center and apneustic center. Autonomic control of breathing. You keep breathing when you're in deep sleep, don't you? That's your brain's autopilot, all right? That's your brain's life support system. Your medulla actually tells the pons what to do. So the medulla is actually in control of everything. So it has some of the reticular activating system. It controls the muscles involved in sneezing, swallowing, gagging, and vomiting. All right, those are pretty important functions. Yes, it's a place where motor control crosses over, but that's anatomy. But the medulla has a respiratory center that does what it sounds like. It controls your breathing. It'll actually control the pons and tell it what to do. Okay, question for you, because we've covered this. Chapter 1, regulation of blood pressure. The medulla controls blood pressure. Okay, what does the medulla do to heart rate if blood pressure is too low? Goes up, right? And opposite, if your blood pressure is too high, your heart rate will go down. That's because the medulla has a cardiac center. All right. Will it do things to your arteries too to correct blood pressure? Because it has a vasomotor center. And I'll put the parentheses around these two. Control BP. So you already know that the medulla does this, but now you know these are the autonomic centers that control the heart, that control your arteries. Okay, we'll pick up and finish this on Monday, and I might start with peripheral nervous system. So I'll try and get that PowerPoint up. Have a good weekend. It's going to be beautiful out. I hope you get to enjoy it.